Hi, my name is Christopher Padilla. This is video 3 for ME210, Power and Efficiency on Chapter 14. Now, this problem involves gantry cranes, and specifically these cranes are the ones that move containers between trains to trucks, then off to stores, or from dry docking situations, as the bottom photo shows, to truck traffic. Now, with this specific container, or with this specific problem, a 20,000 kilogram container is being unloaded from a train. The gantry crane that's lifting the container uses a series of cables, pulleys, and motors in order to lift the heavy container. Now, this specific gantry crane takes 7 seconds to raise the container. If the power supplied to both of these motors is 1200 kilowatts, what would be the upward acceleration on point C that's located on the last section between the pulley and the motor if that same point has a velocity of 2 meters per second? Additionally, what would be the efficiency? Now, as you can see here, the givens for this problem are a mass of 20,000 kilograms, gravity of negative 9.81 meters per second squared. We don't know the acceleration yet. The velocity is equal to 2 meters per second in the upward direction. And the total power for these motors is 1200 kilowatts. Now, as you can see here in the diagram, we have our datum lines sectioning off between point C and the top of the pulleys, and then from the top of the pulleys to the bottom of the pulleys, with SC and SC labeling them respectively. Additionally, as you can see here, the pulleys are labeled in orange and the motors are labeled in purple, with the C point being located between between the pulley and the motor. To start off, we use our equation of motions, um, or not our equation of motions, but our datum lines to create an equation that's equal to SC plus 4SA is equal to the total length of all of the cable. And we can equate that to velocity, which would be equal to velocity equals velocity of C plus 4 velocity A, and that would be equal to 0. To reduce that, we have our velocity at A is equal to negative velocity C over 4. Moving on, we have our free body diagram and our inertia diagram. For our free body, quite simple. We have our weight of mass times gravity pulling down, and 4t pulling upwards. Additionally, for the inertial diagram, very simple, just mass of A times acceleration of A going upwards. Next, we would be finding tension with our equation of motions, and since we know that our sum of the forces in the y for the free body diagram is equal to the sum of the forces in the y for the inertia diagram, we're able to equate that 4t minus 20,000 times 9.81, which would be weight, is equal to 20,000 kilograms times acceleration in the A. Since we don't know that acceleration yet, we can go ahead and find that with kinematics, with quite a simple kinematic equation, which is velocity equals velocity initial plus acceleration that's constant with t. We would be substituting in uh, previous values for it. Resuming, after that, we would resume with equation of motions and find t. Since we are able to find the acceleration being 0.29 meters per second squared, we find our tension, but a key thing that we have to remember is that we have to divide by 2, as we are only calculating for half of the machine when we have to solve for the entire machine lifting capacity. So each cable would be experiencing half of the tension that's found, but it's calculated, as there's twice the amount of cables. Next, we would be determining the power supplied by the motor, and that's given by the equation force times velocity is equal to power output. So we have our tension multiplied by our velocity, which is given as 2 meters per second, and we are given a result of X watts. And then finally, we would be determining the efficiency. Now that equation is power input is equal to power output divided by efficiency. Another key thing to remember is we have to convert kilowatts to watts, or else we cannot do this calculation, or we'll leave the wrong number. So it would be equal to 1200 kilowatts is equal to our X watts from the previous step divided by our efficiency. Reducing down, efficiency is equal to X watts over 1.2 million watts, and that would be equal to our efficiency. That's not calculated in this situation, but